So, how are you doing, everyone? How was the assignment? You finished the assignment, right? Okay, the old one.
Yes.
Do you want a new one?
No.
No? Okay, inshallah. There will be a new one, inshallah. Just to get you moving a little bit. Midterm exam next week. Ready?
No.
No? Good, very good. That's the spirit. Today, inshallah, will also be help sessions. So the exam is on Monday. There will be no help sessions before that because Wednesday we'll also have another class. You already had a help session last Monday, so that it's too many help sessions are not will spoil you. So what I'll be doing is that we're gonna have an extra office hours on Sunday, inshallah. Okay, so if you want,
Regarding the questions, what should we do with the questions?
I was gonna show you today. You're gonna see a little bit.
There are many questions. So
Yes,
what
that's
should we do with them?
use them. Should understand them. We will not ask on deriving them. We didn't discuss deriving them, but you should be understanding what each equation means, how to use it, and I'm gonna show you now today an example, inshallah.
So there will be numerical problems.
For the equations, yes, definitely it will be numerical
So there
problems.
is a problem sheet.
There's a formula sheet. Okay. Alaikum assalam wa rahmatullah. The first assignment, you were practicing this idea of developing or writing, given a description of an MDP, you were writing the state transition probability. You were evaluating the value function by taking, for example, all of these possibilities and so on.
So we have some questions about equations. Yes. How can we solve?
Right now. Don't worry.
What about the pseudo? There was two pseudo.
The pseudocodes, you should know how to implement them. So what you should expect in the exam, inshallah, this is why this will be a topic of assignment number 4. I'm going to post soon, inshallah. You're going to have very small problems, such that something that can have like 3 states and 2 actions, or 4 states and 2 actions, such that you can really have it written in front of you. You can see everything. It will be just a very small toy problem, and you need to be able to do these iterations, right, to implement the pseudocode on paper.
We'll solve it today.
So I'm going to show you something today. What you're going to have is that you're going to have the code that does this for a generic, okay, grid world problem. This is the topic of today, inshallah. And now, you can play around with it to make it the same as in the assignment. So the assignment will be something that you do it on paper, and this will be actually so the code today will be your solution to the assignment. Okay, if you implement it, in the course of today, you're going to understand this part. Okay. But what's important, that you should be able to do these iterations, to do this calculation of whatever algorithm that you have. You do it iteratively, and you see all of you fill in the table yourself. You do what the computer does.
So
this is very important.
No code in the box, only the pseudocode.
Implementing the pseudocode in the exam will be part of it. Okay. Explanation of the code, all of the codes that we had before, is also included in the exam. So, for example, I give you a code snippet. Tells you, okay, what does this do? In any of the codes that you've seen, and all of the interactive lectures, especially also today. Okay, so you get a very small code snippet, and I tell you what is this doing. You should say, okay, for example, this is calculating the Q function of blah 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 blah, or evaluating or trying iteratively to evaluate the policy pi1, whatever. Okay, you should understand the code and how. I'm not going to ask you to write code. That's not doable, okay, in the exam, but to explain code, this is also included, okay?
So you will give us the example for that, or you say that assignment?
Which part? For the MDPs and for the reinforcement learning, assignment number 4 will be enough.
For the pseudocode.
For the pseudocode will also be included in the assignment number 4. So assignment number 4 will have a lot of written parts where you have to do iterations again and again and just filling in these tables. Something I'm going to show you something similar to that. Okay, so let's start. Another question? No. Last lecture was a little bit tough. You missed it? Okay, bad luck. try to catch up. The reading material on that lecture is nice. Okay, so read it. This was not a bad lecture to miss. But okay, I'm gonna do a recap. This is now recorded because we're gonna have there's first a recap of the previous lecture, so try to catch up. And then we're going to see the code implementation, and this will be recorded for you. Okay, and also the code will be, you'll have it. So now let's start with the quality function. Okay, so we said last time that the quality function defined like this, and you've seen this term appearing in several times, especially in the Bellman optimality equation, computing the optimal policy. We've seen this term appearing a lot. And when you look just at this equation and this function, how it calculates it, you understand it as, you read it as the following. So given any state action pair, so given a state and an action, okay, so given a state and one of these possible actions that it has, the Q function describes the expected return. Okay, so the expected return that I take this action while I'm in this state. Okay, so this is more richer if you remember from the state value function, because the state value function tells me if I'm in this state, what is the value of this state? What is the expected return I expect? What is the expected return I expected being in this state? While the quality function is more richer than that. It tells you, okay, if I'm in this state and I take this action out of the different possibilities that I have, what is the value of this? How good is this action? Okay, and you can see here that the Bellman's optimality equation last time I showed you that in the end the Bellman's optimality equation is just rewritten in this Q with this quality function is as simple as this, and the optimal policy is simply whatever arguments maximize this function. Okay, so this is the picture that you should always keep in mind. Okay, so this is in the end what the reinforcement learning is about, is evaluating or trying to help you navigate this state action tree. Okay, this is different from whatever search algorithms you were used to, for example, in the introduction to AI course before, and also in the next topic when we discuss the search algorithms. We don't have this setting of state action pairs. Okay? Sometimes you just have states and you're navigating this state space, but here we have state action pairs, and this is the essence of the reinforcement learning problem.
So the difference between this Q and the value function is that the value function will be the old action that we can use.
In the value function, you're already having an action chosen. Okay. That's why if I tell you that the A is defined by a policy function, so A is equal to pi of S, and you plug in here A is equal to pi S and A is equal to pi of S. This is simply what the value function, right? For a deterministic policy. The Q means, okay, so the Q is more richer than that. It's not telling you that I have a fixed policy. I'm just in this state and I look at different actions, and this is the quality of them. And an example will explain.
We perform the value function for each action.
For each state pair state action pair. Exactly. For each state action pair. And hopefully this example will clarify it. Okay. So this is just a small snapshot of the big tic-tac-toe MDP tree. We're in this state. Okay. Remember, this is a Markov state. What does again, just a recap, what does the Markov state mean? Very nice. We're gonna have very nice midterm.
The next state.
Yes.
The one only the current.
On the current state. So it doesn't matter what happened before. This is exactly what a Markov state means. Okay. So we don't care about what happened before. That's why it's plausible that we start from here. We have different actions. And the actions, if you remember from the tic-tac-toe MDP, were the X moves, right? So our moves. We have different options that we can take, and there's a probability that we find ourselves in all of these different states, depending on what?
The policy.
No. What determines the probability that I find myself in any of these next states? In the tic-tac-toe example.
What is the state action that I can do?
The action I will take is the policy. But where I find myself next depends on what? On the O player. Right? This is a multi-agent game, right? A multi-agent problem. So X plays once, O plays next, X plays once, O plays next, and so on. So X plays, and you have one of these four options. And O, depending on what O plays, I'll find myself in all of these possibilities. Okay. Now the probabilities here are just put by me. Okay. This is just what you should expect in something like this in the exam, right? Or also in the assignment. So the probabilities here, again, they depend on the problem itself. They're part of with this problem. And here they're part, you can think of it in this situation or in this example, they are part of the mood of your opponent. Okay. Let's, for example, the probability that after I take action, if I take action one, if I take action A1, so I put the X in here, the game ended, right? So I won. So what is the probability that I find myself in this state? The probability is 1, right? Because this is a terminal state.
I mean, after choosing this,
After I did this action, I find myself in this state because the O player will do nothing. Okay, this is the terminal state. So there's a probability of 1. If I play action 2, if I play it here, the O player has 3 different options. Okay? And let's assume that the O player will randomly choose either one of these. He will not aim to win. He'll just choose random. If we play several times and we come to this situation, this player we're playing against will choose different options. Okay, we'll choose them randomly. Okay, so with a probability, with an even uniform probability, 1/3 for each of these options.
I don't know what to like.
It's if you zoom in very much, it will be 1/3. Okay. If you zoom in very much, it's 1/3.
Why the probabilities are not equally distributed?
And generally mean.
No, this example.
For this one, it's 1/3, 1/3, 1/3.
Yeah, but the other states.
The other one, that's why I'm saying it's the mood of the player. You're playing against an opponent that if he finds himself in this situation, he will always try to win, right? And he can play in here and play in here because he will win in both cases. So there's a 50% chance and 50% chance he'll play either of these, and there is a 0% chance he's gonna play this.
So we have different opponents here and here, right?
No, same opponent. Same, but different moods. He's a crazy opponent. Okay, not the usual one you play.
But the assignment, I think we distribute equally. Right?
That's right. Different
So it
opponent.
depends on the
Different
question.
opponent. Exactly. Different MDP.
Dr. What specifies this mode?
Again, this is the environment. Right? Because as you are as an agent and as an ex-player, you're playing against an unknown environment. You don't know. In the assignment, you had a player that was choosing everything randomly. Here we have a different player.
So, for example, we can say that he's trying to maximize the reward.
In this situation, yes. In this situation, no. Right? Because he's just choosing random. He could have always won if he played this. Sometimes he just chooses not to win. He just wants to come on playing for fun, right? Just assume you're playing against an older person. He knows he's going to beat you anyhow. Just let the game play a little more. That's it. This is just the mood. And in this case, he chooses with a 50% chance to not let the game finish, and with a 25% chance to finish the game in 2 times. That's it. Again, you see, this is a typical MDP, right? So now the question is, again, just to practice this implementation of the Q function, what is the optimal value function of the optimal state at this state S bar? So I'm giving this just name S bar. This is just the name for this state. The rest of the states, I call them as follows: S, A, B, C, D, until J. Okay, so these are names of the states.
But the value function from the previous lecture.
Yes, exactly. Okay, so the value function, simply, if in order to calculate the value function, you can calculate it by using this formula. Okay. And this formula tells you do a maximum, right, over all of the state action pairs that you have. And I'm in this state, so I have how many state action pairs do I have for this state? 4. So S bar and A1, S bar and A2, S bar and A3, and S bar and A4. So this is this. What?
We take the maximum.
You calculate first the Q function of each. Okay. In this way. Take a moment to look at it. So this calculation of the Q function is simply an implementation of this formula. So this formula is expanded here. So let's take A1. If I'm in state S bar and I take action A1, what is the probability that I'm going to find myself in SA? The probability is 1. And because this is a terminal state, right? We don't look at the value function of what will happen next. We just take the reward of it, the reward of the next state, SA. That's it. What about the Q of S bar and A2? So the Q of S bar and A2 is the probability that I find myself in B, the probability I find myself in C, and probability I find myself in D, 1/3, 1/3, 1/3. The C state is terminal, so I just take its reward. The B state and the D state are not terminal, so I need to take its reward, and I also need to take its value function, right? Its optimal value function, which is from the next.
So the reward here based on the state or on the action?
The reward here, okay, the reward here, okay, from what we discussed last time, is based only on the next state. Just like what we had in all of our examples. The reward is only depending on the next state. Okay. That's why it appears here. So the reward here depends on the next state. Same for Q for the third action, same for the fourth action. If I tell you what the probabilities are, for example, here they were given. So if you know the probability distribution, and if you know the reward functions, you can just plug them in here. Assume that I give these numbers for you for now. You get all of these forward numbers. You can read them as the following. So the quality of being in state S bar and taking action A1 is 10. And the quality of being in S bar and taking action A2 is 7.5. The quality of being in S bar and taking action A3 or A4 is actually 5. What does a quality of 7.5 compared to 5 mean? What does quality mean?
So
Higher rewards.
More? What's the correct word to say it? More what? More expected rewards, exactly. There is more expected reward, or properly speaking, more expected return. Okay. And you can think of it again, just looking at this diagram, that in this case, if I play A2, there is I lose in one of so there are 3 possibilities. So there are 3 ways how this game can continue. In one of them I lose, in 2 of them I still have a chance to win. When I play A3 or A4, in the 3 options that how this game will continue, I lose in 2 of them here, and I lose in 2 of them here. And there's only one way that I have one chance, so one less chance to win compared to this one. This is why these 2 have a less quality function from this guy. And this one has the highest quality function, of course, because I immediately win. I'm in this state, I take this action, I immediately win. I take the highest reward. Okay. Even one last point, even if you might ask, even let's say that I win in this situation. Let's say for example I win later on, okay, along this path. Why is this quality function better than this one? Because if you remember what we had before, you usually have that when the game takes longer, you usually have a minus reward, because when I play longer, there's a more chance that I'm going to lose. So usually you want to penalize this by putting a -1 reward for each non-terminal state. Question.
Regarding the value function here, for example, V star SP.
V star S, which line?
The second
line?
Yeah, second Q.
This one.
How is it the recursive of the Q or it's independent?
Now this one, do you know it? Do you know this guy?
Value function of this?
Yes.
No.
Okay.
But we have the
Do
formula.
you know how to calculate it?
We have the formula.
Exactly. So the V star of B, of being in state SB, is the maximum of all options starting from this state, applying the Q of being in SB and taking all of the actions from there, which is simply repeating what will happen here, starting from here.
So
You
it's
do it
not
recursively.
SP.
Exactly. You do it recursively, okay? Until you end there where the terminal states.
Can you give an example or did get how will you do it?
Okay. First, just you to apply it in here, you just okay, again what I want to do is assess different things. Like, this is recursive, right? I don't want to assess everything at the same time. It will too much with the code implementation and with applying on a real robot. So that's not what we're doing here. So what I just showed you here is how do you take this formula from a formula sheet, for example, and expand it such that you can get numbers, so that we can assess you, so that you can have one number in the end, okay, for the course. Okay.
In the second line, why we take the reward of SB and then the value function of the SB?
Sorry, that's of course a type. So this should be SD, of course. That's a type. So this should be reward of SD and the value of SD. Yeah,
Yes, this.
no, sorry. That's a type, of course.
No, and the first one we take the reward of SB
Yes,
and then the value function of SB.
yes.
So how this?
It's simply this guy. The reward of SB, remember, we take summation of all of the possible states. We had B and C and D, for example. And then we had a probability of going to either one of these. And then you take the reward of being an SB with the value function of being an SB, the reward of SC with the value function of SC. That's why there's this is what this summation means.
This maximum, for example, if we choose a SP right now,
Yeah,
then we will have also other states
exactly.
below. So we'll have a method like it will count the number of steps and choose the maximum based on the number of steps.
You cannot evaluate. So the idea in the computer, this is what we're going to do today. You cannot calculate this guy unless you have the value function of SB and SD and SI, and that's it. Okay, so all of these ones, which is simply these ones that still the game didn't end with. Okay. G, there's a G there. Okay, yeah, the G doesn't appear because it has a probability of 0. What?
Should be given the value function.
In the exam, I'll give it to you just so that I see whether you can do it. But in practice, what happens is that you still need to calculate something like this for each of these states. Here we started from the S bar. You do the same for SB. You do the same for SD. You do the same for SI and for SJ.
And look, regarding the maximum, you mean we choose we didn't calculate all of them, or
So what is the value function? So the question here, what was the value function itself? So the value function, if you look at this formula, tells you simply this is the maximum of this Q function. So we had different possibilities. We had, starting from S bar, we had 4 possibilities. These are the 4 ones. These are the 4 value functions that we had. The state action or the action value function that we had. So the maximum of these is what?
10.
Is 10. So this is the value of being an S bar. What is the argument that maximizes this function? Is A1. So the maximum value I can get for being in this state is 10 by taking which action? A1. So the optimal policy, when I find myself in this state, what should I do?
Take action A1.
Should action A1, I'm gonna win. Again, if you do the same here, again, if you do this recursively, this action, okay, while being this, let's say that A1 was not there. So I had these different states. So the next thing would be to choose A2, action A2. And then after I take A2, I find myself in one of these 3 states. I'm gonna have the policy will tell me if I'm in this state, do this. If I'm in this state, do that when you do it recursive. So you're gonna get a policy. So the policy in the end will be for all of these different states, there will be an action map to it. This is the policy.
Also, the probability. Why is it 1/3? Should it be 1/4 multiply all the probability?
This is again what you had here in this problem.
we
So
don't-
the probability is part of the problem, remember.
Yes, no. I mean to reach the second state here.
Yes?
It's 1/4. And then to reach one of the
No.
What?
The probability is only, again, this is what this formula means. You're being confused by what's in the previous assignment. No, the previous assignment, there was no state actions. There was only states. Okay, so what you had in the previous assignment, you had going from here to all of these. There was no state action pairs. You see, this is why the Q function is more richer. You look at the actions and the states at the same time.
And here the Q function.
The Q function, here we're evaluating the Q function.
So why we don't consider the previous probability?
Because we hadn't talked about the Q function yet. Just taking step at a time. This is actually what you also had in the previous assignment. Okay. So in the previous assignment, you had going from here to here by different probabilities, no matter what the action is. So we had that the actions were specified by a certain policy. This was the idea.
So here we take the Q function only at this state, the A2.
By this approach, we calculate on the end one value. We calculate 4 Q functions. Okay, because at this state I can take 4 different actions, and in the end, only one of them is the value function, is the true value function of this state.
But this value function is not for this point to the terminal state.
It's not from?
Didn't we have a stage before we go to the terminal state? A1 or B2 or B3 or B4?
This is different from what's in the assignment. Think of it as a new thing. Okay, go back, put both side by side, and then you're gonna see what I mean. Okay?
We have taken an action, for example, SP. So does the quality of supply depend on the quality of SP as well?
Of course, this is what this says. Exactly.
So how can we have a number on that to be dependent on?
You solve it recursively. What we're gonna do today, inshallah. This is the whole idea of the reinforcement learning, right? Ideally speaking, it's a recursive formula. What I'm gonna do next depends on what will happen in the future. This is the simple. It's very intuitive, right? How I'm gonna teach this class today, right? Depends on the value of what will happen at the end of the class. So if I choose make a choice now, and I know the future, I'll choose the best thing for now. It's very easy, very intuitive. Of course, it's a causal, of course, that the current depends on the future. This is why it's complicated, and this is why we're trying to solve it using the computer. And these are the different methods you can do. So what we discussed, again, this is just a recap for your sake, that we discussed the policy iteration algorithm. Okay? Says that if I have knowledge on the Markov decision process, if I know that state transition probability, I know the reward function, I can use that, run it with a computer. Again, very simply, it will take some time. The computer can handle that. And in the end, I can iteratively get the value function, get the policy, get the value function, get the policy, and in the end, it will converge. We're going to implement today, inshallah, policy iteration in the code. We talked about last time about the different model-free algorithms. And one of these actually was the first one we didn't talk is actually the Monte Carlo learning. This is also going to be something we're going to take a look at today, inshallah. We're going to look at not at the Monte Carlo learning, but the Monte Carlo approach in general for the policy evaluation. Again, so this was a recap of the Monte Carlo learning. And again, this is what you're going to have in the assignment to implement, because it's very simple. You interact with the environment repeatedly. At each episode, you just record a number of state action reward pairs. So this is what you get. You take one step, you're at this state and you took this action. This state action, state action, state action. So this is how you evaluate. And at the end of the episode, this is what the Monte Carlo does. So at the end of the episode, after it reaches the terminal state, looks at everything it passed through. It takes the summation of this, just takes the return that it had from doing and from following this path. And the Q function in this perspective, you can think of it as a giant table. It's a function of the S and the A. So it's a two-dimensional tensor, just a matrix. And if you think of the rows being the state and the A being the actions, what will happen here is that I pass in one episode, I pass through, for example, this guy and this guy, this state action pair and this action pair. And so I can now, I evaluated these. I know what the environment will do if I reach there, at least in this first episode. And what will happen is that you play different episodes. So in the first episode, you've visited these states and you've taken these actions. In the second episode, you've visited these states and taken these actions, and so on and so forth. Repeatedly, do it 1,000, 2,000, million times. Okay, but by the law of of large numbers, you're guaranteed that, okay, if you do this large enough, you will in the end converge to the true value function. And the Monte Carlo learner was updating this, had this update law. Okay, and this is something you're going to always see. So this is as easy as it gets, because in the end, what you just have is that in general, you have something like this. You have a new estimate is equal to the old estimate plus a step size. So it's just a learning parameter that you have inside of the code. And you have some sort of the target. And in this, for the Monte Carlo, we had this kind of target, and we minus the old estimate. And we've seen last time the temporal difference algorithm and the other, for example, SARSA and other algorithms, they just have different ways of calculating the target and different ways of updating the estimate, but it's usually this case. Okay. So this is what the reinforcement learning does. Now let's look at the code. Yeah, and this is just what we discussed about last time for the Monte Carlo learning. Now let's look at the grid word example. Now let's go to the code, dive into deep. Again, this is an interactive notebook. So whatever you want to see, just let me know. We can play around with it. So let's see. Let's hide this guy. Should hide. Okay, so the code, you're gonna have it similar to last times. You can read it, all of the details you can read at your own pace. The use of the code for our purposes is, yeah, you're gonna see that it's straightforward, but there's a lot of stuff that are depending on it, because actually we're using here an implementation for the grid world. Okay, so this implementation is already on the internet. I here acknowledge the person who did it. Actually, it's a very nice implementation for the grid world. I'm not gonna tell you all of the details in here. You can take a look at this code, but again, just for this part is just an implementation. If you're interested, you want to look at what's going inside, go in and dig deep to it. We just want to use it today. That's why I'm gonna just hide it from here for now.
Look, what part of the code are we gonna ask?
Starting from here. Okay. So now what we're gonna do is that we're gonna implement our grid world. Okay. The way we're gonna implement it is the following. So here, this is the grid map that we want to implement. Okay. I'm gonna show you in the end what it looks like, because yeah, you've seen it. This is what we've been working with. Is this clear? Is this big enough? Let me try to hide this one. Okay. Let me try to. Okay. Let's see if we can remove this guy. Okay, this is better. Okay. So this is the grid map that we have. Now that we need to actually zoom out, see the whole grid. Okay. We've been working for this for a while now. Again, so this is what we called as A, B, C, and D, E, F, G, H, I, J, and K. We've been working with this for a while now. So this is the obstacle. This is the +1 reward state and +1 terminal state, and this is the -1 terminal state. Okay, so this is the treasure, and this is the mine or whatever. Okay. So how we implemented this again? So you see here, we're building an instance of this reward grid world, and again, this is a class someone else implemented, so we're just using their code. And for this purpose, we defined the grid world, the grid map. So we said, okay, we want it to be 0, 0, 1, so 0, 0, 1, so 0, 0, 0, 1, 0, 3, 0, 2, 0, 0, 0, 0. Okay, so this is how just we initialize and say, okay, we have this map.
What's the name?
This is where we want to have empty space, where we want to have an obstacle, where we want to have a positive reward, and we want to have a negative reward. Okay.
What is the number? Is it 3, 0, 1?
The 0 is empty cell. 1 is a positive reward. 2 is the red block, right? This mine, and 3 is just an obstacle. With this implementation, actually, as we're going to see, and then we can actually build even random, more complicated maps. You can just do more of these. Okay? You define the map. This is the one that we've been working with. And here, this is just a naming. Okay, so we just call, because again, everything in the code for the actions is implemented as 0, 1, 2, and 3. So we just transform it into up, right, down, and left. And for the states, they are also 0, 1, 2, 3 up till I think 10 or 11. So here we just call them with these names. The transition model, if you remember, the probability transition model of this problem is that if I take an action and I go in a direction, there's an 80% probability I'm going to go into that direction, and there's a 10% I'm going to go either to right angle to the left or right angle clockwise, right angle counterclockwise. And this is just a policy that I specify. Again, so you specify what the policy is. In this policy, I specify it to be right, down, and blah, blah, blah. Okay, so we just specify it. And in this case, you can, with this line, you can actually visualize this policy. So I'm going to show you this policy that I drew.
Transition deterministic.
This is the same as the indus sign. Exactly the same what we've been working. The probability distribution is definitely stochastic, but the policy is deterministic. Okay, that's why what you see here is that if I'm in this state, the policy tells me to go right. If I'm in this state, the policy tells me to go right. If I'm in this state, the policy tells me to go right. If I'm in this state and I go right, am I guaranteed to go here? No, not in general, only with an 80% probability. There's a 10% probability I'm going to go to the left, stay in the same state. 10% probability I'm going to go to the right, which is right of where I'm going, and I'm going to go down. Okay, so this is what you've been working with. What you see inside of here is the solution of assignment number 1, what you had. Okay, so these were the tables that you were filling in the assignment. Okay. So this is the state transition probability given that I take always up. This is the state transition probability given I always take action right, and so on. Okay. So these were the tables you had to fill in. So you have now the solution. You can go look it up. What we're going to do is the following. So we're going to execute the policy pi1. What is pi1? This policy that we drew in here. This is also what the same that you had in the assignment pi1 and pi3, right? This is the same pi1 you had in the assignment. So let's execute it in the sense that let's run it and sample randomly what will happen. Okay. So what this code does is that, okay, we always start from SH. So state SH, if you remember, was this guy here. And we're just gonna take random samples. We're gonna follow the policy, but because it's stochastic environment, we're gonna have different episodes. Okay, so we're gonna ask for 10 episodes from here. We use the problem.execute policy. We tell it, okay, I want to follow this policy. I want to start from this state. So this is the state row 2 and column 0. And I have a gamma of 1. So I'm calculating here what? The return, exactly. And in the end, it just returns this return that it calculated in the episode. And I'm just gonna visualize it. And what you see here is that in the first try, it took episode SH, SHE, A, B, 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 SD, CD, sorry. And the second one, okay, you see what's happening. And you get the different returns. Okay. You have a very good practice with this for now. You chose in the assignment your own randomness. You did the sampling yourself and you calculated the returns. Here you can do it for different gammas. If we change the gamma here, we're going to get different numbers. You can play around and see what happens. Now let's look at the estimation of the state value function. Everything we're going to do in this code now is only talking about the state value function. We're not going to talk about the quality function, which is the action value function. We're going to only look at the states. So I'm in this state. I want to know the value of it.
The one that include
the V of S, exactly.
And the equation there is the one.
Exactly.
How did you tell the code that it should stop at SD?
Sorry?
How did you tell the code that it should stop at SD?
Because SD is a terminal state.
So why not the other one? You have to. So why?
You mean why it always ends at SD? Let's see. Always SD. Let's see. Again, I have no idea whether it will happen or whether we're actually, it's just, again, depends on the probability, right?
Yeah, so
This is completely random. Okay, do we get anything SD? No. I'm not sure we're gonna even get SD. Let's see. Looks like, yeah. Let's see. Okay, you have the code, right? So you can run it as much as you want until you reach the other state. But again, if you remember from last time, the probability that I reach here is that I come to this state, and then I take a 0.1 probability to come here, and then another 0.1 probability to go here. So it's very, very low probability, okay? You need to run it several times so that you're reaching this. The Monte Carlo simulation is the following, okay? So what we're gonna do is that we're gonna, for 10,000 simulations, we're gonna do 10,000 episodes for each of the states. So I'm gonna start in each of the states once. I'm gonna do 10,000 episodes. I'm gonna calculate these 10,000 returns. I'm gonna do what in the end? Just the average. This is what the expectation does. So this is what the Monte Carlo. So this is literally just coding in that the fact that the value function is equal to the expected of the return. Just the equation of the definition of the value function. And we're doing it with the computer. So this is why it's called the Monte Carlo simulation, because we're doing this for a large number and we're doing it with the computer. Yeah, question?
The same policy, but we start with different state, right?
Same policy with the first state, exactly.
So we don't start from SH always.
No. When we're doing the Monte Carlo simulation, okay, if we start always from SH, we're gonna get, and we average this, we're gonna get the value of SH. Now we want to get the value of different states. We just start from a different state. Okay.
So, the Monte Carlo will evaluate all the states.
The Monte Carlo, because you want to get the value function for all of the states, the Monte Carlo, just as the name means, random sampling, okay? And then until you reach the terminal states, and then you just do it again and again and sum these, average these numbers, okay? And this is what this code just says. And let's see that the number that we get in the end. Again, this will take a while, of course, because it's 10,000 episodes for each of the different states. So now it reached SH, SI, SJ, one more to go. And in the end, it will give us these numbers, which is simply what? The value function, right? Just an array of numbers of being in these different states. The value of being in a state, this one, SD, is 1, and the value of being of this state is -1y. These are terminal states. This one has a value of 0. What do you think this one is? That's exactly. This is the obstacle. Here in the code, it's much easier to actually include the obstacle, because otherwise it's much easier for the mapping and so on. So this implementation includes the obstacle as one of the states and always takes care that it has a probability of 0. So if you start there, you always remain there, but you never reach there. So this is one way of implementing that. I call it here as X, and you will never reach it. Okay, here. So this as X. Okay.
It's written down there, is X.
What?
In the array.
In the array, it's in the array. You will find it in the. This is index 0, 1, 2, 3, 4, 5. So index 5 is the obstacle. So if you go here, index 5. So 0, 1, 2, 3, 4, 5. So this is the obstacle. Okay.
So we have a larger dimension.
For the calculations themselves, it's exactly the same. This is just a code implementation. Yeah. So here, yes, we have a larger, like we need a larger memory size because we're taking obstacles into account. But when doing the calculations, we never reach this state, and we never do anything with it. It's just like a bookkeeping. We're just keeping there so that the code is much neater. Okay? Otherwise, you'll have to remove it, right, and play around with the code.
For all these states, we reach the SD, the terminal state.
No, I have no idea. No. Of course not. I don't even expect it. Otherwise, how do you get these very low rewards, right? You can think about it. These are very low rewards. So
since it's not negative, that means it's at least reach SD.
By the way, you're taking the average, right? You're taking the average on all of these different episodes.
But no way to get positive reward unless you reach SD. Otherwise, you will be.
What? Okay, so what you're saying is that in these states, like I don't reach. There are sometimes I reach SD and sometimes I reach H. The other one.
Will be reaching this D.
For the high ones, yes. For the low ones, no.
How can
How can be negative? How it can be positive?
Because of the average. Because again, you sum of different ones.
some negative?
Yeah, it's a negative number, so not.
It's a good point. Let's see.
Well, each step is minus 0.04, so it's possible because.
Then you like have that's a good point.
But if you can go.
I would say that the reason is, for example, you see here that, for example, that we have a gamma. Okay, we have a discount factor. Okay, so the further we're going along the episode, the smaller the number begets. I would say this is the
Negative.
What?
It's negative still.
But you sum it to a large number. Okay, so in the end, when you reach the 1 again, so remember we had the minus 0.04.
Even if we go with all those one, we reach negative because minus 0.04, and then even SG is minus 1.
SK is it's near SK, right? You can go to the map.
Yes, that's right.
So it is this is why we say this, because it is the nearest.
We can do something. We can do something, but to let's see. Let's just try it out. I'm gonna make this last step, this last action up. Okay, so this one is up, so it has a very high probability actually going from here. I'm gonna also make this one, instead of being up, I'm gonna make it right, and let's play around and see. And if this messes up the code, we're gonna stay longer today, okay? Because this goes right. Let's take, let's see if this works. Okay, negative numbers. Okay, happy now? Yeah. Okay, let's see. Undo this guy, undo this guy.
The environment here is terroristic, not populistic.
Oh, no way.
Because it's never gets negative. None of the state.
Again, this is average. That's the point. You're taking an average, right? So you look at all of the different possibilities, right? With this, and again, for this policy, not for any random policy. You can try it actually with a random policy. If you see here, I added for you this line. You can play around at home and actually initialize it with a random policy, not with this pi1 that we had in last time, because this pi1 is actually very nice because like it leads always to the goal state. But if you start randomly, you're gonna see a lot of negative numbers. Okay, so we did this guy. Let's do it again. It's quick. Do Monte Carlo again. And now the next part. Okay, so here this is supplementary for you to play around with. You're gonna find the solution of assignment number 3. Okay, so this is the solution of assignment number 3. Yeah, we're gonna find everything there. So here we had the policy pi3. Okay, and this is okay for you to play around. Now let's look at Bellman's equation. So if you remember from last time, Bellman's optimality equation, okay, of the value function of the Bellman's optimality equation is a representation of the V in terms of itself, right? So if I expand this, I can have a recursive equation. Again, so V is just a vector. So I can have a vector written in terms of itself. So I can do what? I can just do matrix inversion if I have the P and so on. So this is exactly what this will build up in here. So what you're going to see is the following. Again, I'm going to leave for the details for you at home. But with this line here, I tell it, give me the probability of policy 1. This probability here is usually what you did by hand in the assignment in terms of a tree diagram. So when you have a tree diagram, you already assumed you already have a probability, you already have a policy in mind that you chose. And then you find yourself jumping from one state to the other depending on how you follow this policy. This is precisely the probability distribution inside of this line. So if you want to check, for example, you want to check the solution of the tree diagrams that you had in the assignment, write the policy for it, check this guy, and you're gonna find the numbers that you go from one state to the other. Okay. What? So here, this is the probability of following P1, yes.
What is the V1?
What?
What's the V1? What is
P1 is what we had in here, this guy. The same P1 that you had in the assignment. Sorry, pi1 that you had in the assignment. Okay. What else? Here I just do some stuff to remove this idea of the obstacles, because the obstacles, they were available and they can when you include them in the Bellman optimality equation, you're gonna get some wrong stuff. So you just need to remove it. This part is very important. Okay? I just need to look at it for a second. R1 is the reward function that I have, and P of pi1 is simply the probability distribution of following pi1. Can anyone tell me what this guy is doing? It's multiplying the probability distribution by the reward function. If you remember from last time, the reward function, this guy, was when I reached the state. And the probability tells me whether I reach that state or not. So this reward function, the expected reward function, is the reward of being in the current state. Remember this discussion we had last time of the reward being outside the summation and inside of the summation, what we did? So this guy is inside of the summation, this guy is outside of the summation. Okay, take a look at it, and also when I'm gonna add some like explanation stuff here, this will make it much clearer.
So this is the reward of the current state.
This is the reward of the current state, exactly. You see, the reward of the current state depends on the reward of the next states and the probability of when I reach them. And then in the end, the value function, okay, is calculated by this equation. It's the inverse. So we invert the matrix multiplied by the R, the expected R, and the matrix that we have is simply identity minus gamma multiplied by the P. This will be much clearer, okay, when you see the formulas itself, but this is simply just a matrix inversion. You write the Bellman's optimality equation as a matrix and you invert. That's as easy as this. So this is as easy as, this is one of the easiest way that you can create the optimal value function, and this is the optimal function, the optimal value function. Okay. And again, this is the optimal, the value function of this, okay, of this policy. Let's see. Now let's try to replicate this guy, but now here we solved it analytically. Now let's do it iteratively. Here we're going to do the iterative policy evaluation. So in the iterative policy evaluation, if you remember, we use the Bellman optimality equation like in here. But the trick is, and this is what you're going to also experiment with in the assignment, is that when you let's see, maybe let's go to this part here. So when you implement, let's say that you want to do this iteratively, and you find yourself that you want, for example, to have the value function of the next state. Okay, one very easy way of doing this is when you do this iteratively, is take the old value that you had, okay, from the previous iteration, and just plug it in here, and that's it. So this is the idea. So this is the idea of the iteration on the policy. What? So what this algorithm does, okay, let me go back to the code here. So you see, it loops over all of the states, and then it calculates the value function of the current state it's in based on the value function it has right now for the other states. So it's not doing it recursively, right? It's just what I have now, I calculated by the old one. Exactly. The old one is not the correct value function. It's just a number. It's just an estimate that I have. Repeat this several times, it will get better and better and better. That's the whole idea.
Why the other state? Why not the current state, the state that's on now?
Because the probability distribution, okay, if you go back here, let's go back here. Okay, so the value function depends on the value function of the current state depends on the next states. And how am I going to reach the next states when I multiply by the probability distribution?
So the next state, not the other states.
The next states I'm going to reach from the other ones. In principle, I'm going to reach all of them, but many of these will have a probability of 0. That's why in the code, it doesn't matter. Okay? So all of these will have 0 multiplied by stuff, but that's why you have this, you have to sum over all of the states, but there's again, even in real world, if I'm in this state, there's the next action I take will not bring me there, right? So there's some sort of locality, right? I only reach a small number of states around me. Again, so but when you write the summation, you write it around all of the states, and the probability will have so many zeros. That's also what you saw in the assignment, right? There are so many zeros because I take the probability of going to all of the states. I consider all of the states I'm going to. Okay. So this is why the iterative policy evaluation like this. It's just a numerical method, just an approximation to solve this. It works nicely for small problems. When you try to do it for large problems, it doesn't work. And you see here, after a few iterations, I didn't count how many. You can count how many iterations this took, but in the end, we reached the true value of the value function. So this is you can think of this is the ground truth. This is the true value function that we calculated by doing a matrix inversion. So this is analytical. So we have the correct value function. What? Of course, this is small dimension. Yeah, you can still use it again because you can also try to solve a linear system of equations. So AX equal to B in this kind, and this works up. I would say up to 1,000, maybe 10,000 or something. You can do it with a computer. Larger than that doesn't work. Okay, and again, you need to know the MDP. You need to have the model of the probability. Here, of course, we're using the model of the probability distribution and also the reward function. In general, you don't have it. This is what we were discussing last time. So you see here this value function that we got using the matrix inversion, using the analytical value, is almost the same as the one that we got this iterative.
What the advantage of iterative value?
If you cannot have a matrix inversion for any reason, you just do it iteratively. Okay, again, based on this trick, you can think of it this way.
So we have done the same thing in two different ways.
Yes, well, we're gonna do it in even more than that. This is what again, you remember, this is just a toy problem, right? You want to learn the algorithms based on something that you know its solution. Right? You don't want to learn a new algorithm based on something you don't know the solution of. Otherwise, you don't know whether it's right or wrong. That's the philosophy. Here we're gonna do now this is our first model-based reinforcement learning. And this is what the policy iteration. If you remember from the policy iteration, we had two different things. We had the iterative policy evaluation, and there's the policy improvement, right? I try a policy, I evaluate the value function. I take this value function, I improve the policy, and so on. And this is exactly what this will do. Again, there is here an implementation, okay? Details for you to look at home, okay? But again, what this just does is simply we use it in this way. Again, just like you can think of this similar to what we were doing with Keras, right? You do the code or find someone else who did it for you. This is you're gonna find in I'm not sure in TensorFlow that they have this algorithms also implemented, but in OpenAI Gym, for example, they have these reinforcement learning algorithms. So you can just in the same way that you run it like this, you just initialize a solver and you train it and so on. So here, yeah.
Here you said it's model based, but before also we have the model.
Again, so everything today we have a model. Okay. The first step says, okay, you have a model. Can you solve it precisely, analytically? The answer is yes. We can just do a matrix inversion. Matrix inversions are always bad because they scale to the cube of the dimensions. Right? So if you have an n by n matrix, okay, and you want to do the inversion of it, if this n becomes let's say 10 times bigger, the computational complexity of this matrix inversion is 1,000 times slower than doing it for the first problem. Okay, so it's a cubic order of magnitude. That's why people try to solve these matrix inversion or try to solve linear systems not using matrix inversion but using iterative methods. This is the idea. The policy iteration gives you in the end the correct policy. So now we're gonna solve it, and here again you can play around with it. I'm gonna show you here some stuff, okay? Because this is what's going on in the iterations. You can look at it at your own pace. In the policy iteration, we're gonna start with the value function. Okay, so the arrows here specify the policy, and the numbers you see inside here specify the value of each state. We start with an unknown. Again, this is unknown, so we start with a value function of 0 everywhere, and we start with a random policy. So we initialize here this to be a random policy. This is not the pi1 that we started with. We don't know it. We don't know that this is pi1. It's a random policy. You take this random policy, okay, and you know that you can evaluate the policy, and you get these numbers. Again, we don't solve it precisely. We just do it iteratively. So we get numbers. Are these the value, the correct value function of this? Of what? It's estimation of the value function, yes. Okay, but it's good enough. How many iterations did we do to go from here to here for this to converge? We took let's see if I have some numbers here. And again, these numbers are available just for debugging. We took, in the first case, we took 8 iterations. So for this random policy that we started with at time equals 0 or at the first iteration, we had to do 8 iterations such that the value function converges. And now it started to converge. So the value function is not getting better and better. So you can consider that this value function is a good estimate. It's not a perfect estimate, but it's a good estimate.
But at the beginning, you said that we will estimate, we don't have a policy, so we will take random policy.
Exactly.
And also we will take random value.
We started with the 0 value function, yes. This is what we did. After the first policy evaluation, the iterative policy evaluation, we got this. We got a value function for this policy. So that's why if you compare this and this, they're the same policy.
Isn't it one iteration or one thing?
What?
Isn't it one iteration? Why is it the same?
It's because when you calculate the value function, you have to iterate.
Prove the one.
No, when you calculate the value function for a given policy, just like what we did here, and this guy, there was an iteration here to calculate the value function because we're not doing a matrix inversion. We're trying to
We just converge the value, not
converge the value of the value function.
not improving the policy.
Nothing yet. It's the same policy exactly. And after you get this improved after you get this better this calculation of the value function for this policy, I can use it to improve the policy itself. How do we do that? It's as the idea is the following. So I'm in, let's say I want to have a better estimate of this action here. So this action that I'm in right now tells me to go to left, right? So if you're in this state, which is better, to go left, down, or right? Why?
Good.
Exactly. Because this, the expected reward, the expected value, the value of this state is better from these two. So I just make this right. Okay?
How to know what's better? Calculate it.
I have these numbers.
You have it's one, but how the code understand that?
It's better. The max.
So the
Now, the maximum of 1 minus 0.2 minus 0.08 is what? Is 1. What is the argument that gives me this maximum number? Is right. So it knows that I should change this policy to be right. This is the idea. Okay, let's try another one. I'm in here. So I go down, or I go to the left, or I go to the right, or I go to the up. So I need to look at all of these. What is the value function if I go to the right? Sorry. Okay, the right of where it's looking at. I'm gonna rephrase this. What is the value function if the policy here is right? What is the value if I take a right action? -1. What is the value if I take a left action? No. Minus 0.2. The same value because the probability tells me I'm going to stay in the same state. What if I take up? I reach this number. If I go down, I take this number. So what do you think the value will choose?
Up.
Okay. And so on.
So this is what was meant by the max Q.
Exactly. This is what the max does. It does all of these calculations and then it improves.
But why it's considered the above value? Even it's higher, but it cannot go.
It's because the above one is a lower negative number. So it's a higher value. It's a lower, it's not taking an absolute. It's not talking about the absolute value. It's taking comparing them from minus infinity to infinity. Okay.
Doctor, you said that the obstacle is -0, right?
The obstacle, yes, the obstacle doesn't exist.
Why the value function is not -0? Why it is
The value function, we removed it from the code. It was like we write it just as a code implementation. We include it such that it's easier to have like you can, as you're going to see actually in the next part, we can use the same idea and we can build bigger maps and so on. So it's easier to do iterations over all rows and all columns, right? But if you have missing rows and missing columns, it will be nastier in the code. This is the idea. But okay, so but inside of the code, it doesn't exist. That's why when we're thinking about it in terms of the state space, it's only these guys that exist. This doesn't, in the MDP, it doesn't exist.
So we cannot put the arrow to the left, right?
No, you can take a left action. Why when you're in here, you can take a left action. And what is the probability after if you take a left action, right? This action has a value. And then you also compare it.
This value is higher than going up, right?
But this is the value is not 0.
Yes, it's -0.
No, the value will not be 0. Okay, it will depend. Okay, how you calculate it. If you go left, you might find yourself ending up either in here or in here or in here. You take the expectation and so on. Okay, so the same ideas. Okay, so taking an action doesn't mean you're going to be in that state. There's a probability you're going to end up in different states. Again, this is the same game. And in the end, iteration after iteration, in the end, you reach this state, this policy. Now let's look at the let's see whether actually, because this is reinforcement learning. That's it. We've done it. We've solved the reinforcement learning problem. We have a policy for this MDP. So if I'm in this state, I take this action. If I'm in this state, I take this action. If I'm in this state, I take this action. So let's just do it with our minds. If I start in here, okay, the best thing to do is to do like this. And there's a high probability I'm going to actually follow these states. But at some points I might, like, maybe if I start in here, I find myself going there, right? If I do that, there's a high probability I'm going to follow this path. So you can draw these lines in your mind now. Okay, so this is the optimal path from here to here. This is the optimal path from here to here. Can anyone explain what's going on in this guy? Because it doesn't seem intuitive, right? Why isn't this looking to the left?
Because -1 is the lowest. So it's
There is no
Exactly.
possible to reach -1.
Exactly. So it's very smart. By always doing down. So if you actually have a robot that's navigating this environment, if it tries to go left, okay, it found out by experimenting that there are many times I'm actually going to go to the right, okay? But when I try to go left, there are many chances I'm going to go up, okay? So this actually has a worse reward from just starting from here and bumping into the wall until I jump into this state, and then I'm going to follow this one. So it's a smart agent.
But why before we consider only the most only one direction that we can go, and then here we also consider the right direction.
Sorry again.
If the direction to the left.
From this state.
Why not consider only this one? Consider also the -1.
Because of the probability distribution. If I'm in this state, I take an action left, there's a 80% probability I end up in here, 10% probability I end up in here, 10% probability I bump into the wall and I come back. Right?
So the highest is to bump the wall.
The best action starting from here, given the probability distribution of the whole map, is to do this. Okay. Now I give you two other examples. So this is actually one nice one. I'm just gonna show it to you. Let's see, try to get it very quickly. So here the code also allows you to actually build the map that you have in a CSV file. Okay, we're just gonna put it here in the Google Drive, and now we're just gonna actually no, we had it. I had a different name here. Just rename this to be world big.csv. And now let's run this guy. Now let's look at this. Will take a while, of course. You're gonna see why. So now this will be a huge map, okay? And this is again policy iteration. So first we initialize the grid. In this part of the code, we just take this CSV file and make it into zeros and ones. We read this CSV file and put it into a map, and we run the solver. We initialize the solver to be the policy iteration solver that we just did, and we just train it. It will take much longer time because this is actually the map that we're playing around with. Okay, so you see it's huge. Okay, so this is something you can play around with, that you can look at it at your own time. Let's see. What I just want to show you is let's end up in the last minute with this part. Is this the optimal policy? Let's see. I'm trying to just to. Okay. Yep, this gets told. Okay. Is this the optimal policy? So again, you start in here, for example. You'll find that you're gonna follow this path, like here, this guy, and then from down, you're gonna reach here, okay? So this is a robot trying to solve the maze, okay? So you see, it's actually smart. So if you randomly start at any of these points, you're gonna actually find that this is a very, very smart way of actually solving this maze, except in this region.
At the bottom, if it's up, it will be
Here again, this random behavior that it's doing actually is because in order, you remember, to avoid these
In the
these
middle,
lines.
take all the line.
What?
Middle top, take all the line.
Where?
No, bottom,
Here?
at the bottom, yes.
Here?
The last,
This one?
Yes.
It does like this.
if it's up, it will be better.
Again, this is what it calculated. This is a very good point. We converged on an optimal value function, but the optimal policy itself is not unique. So you can have different policies that give you the same value function. So this is why this is something in general for large MDPs. I just want to check this guy. If I start in here, okay, there are no red blocks in here. So the optimal thing should have been what?
There's no green, so there's no.
What?
There's no green.
But it tries to reach this guy, right? So actually it wants to, you could have thought of something like a better policy, especially in this region, that, for example, it always goes to the right or always goes down until it tries to escape the maze from here. Because inside of here, okay, if it goes down here, for example, it doesn't escape the maze. And also from here, for example, it's trying to bump up in the wall. Why not just go to the right, and follow something like this? Is this the optimal policy in the end? Why?
Because there is some action that's not intelligent.
It depends upon the persons of the terminal state.
Maybe because it's not why not.
Take a long time actually.
Exactly. This is the point, right? So the policy iteration, again, we ended, if you look at here, so you can take a look at these curves at your own pace, but we wanted to have 500 epochs in the end. So we only did 500 number of going from policy evaluation to policy iteration back and forth. So, okay, it was a policy improvement back and forth. We did only 500 of these. And each one of these had also internal iterations, but we only did in the end these general 500 ones. But maybe 500 is not enough. We stopped the code at 500. Maybe we needed actually more than this. Because if as you've seen that the states near the terminal ones, they get better, they get better and better very quickly because they're near there. But as you go further and further away from it, along the tree, you need more iterations because there's some recursiveness being
And
had.
also the gamma, we start from far away, it will be.
Absolutely. The gamma plays a very big role here. Here we had the gamma, I think, of 0.999. Try playing around with the gamma and see what happens. But all of these are some factors that play around with. So the bottom line is that, you see, even though it works for the small problems, I can tell you that this is not the optimal policy. A better learner actually can actually solve this part of the maze because it's very far away from the terminal state. Okay? So you can imagine that in the game of chess, these are the terminal states, and this is where you start with, for example. This is where the game starts. And you take a long time, you play a long region, you play a long time, and in the end, when you're near the terminal state, it becomes easier and easier because there are less choices to make. But at the start, there are so many choices to make. Okay, so what is the best thing to do? So inshallah, next time we're going to see a better learner, okay? So maybe, for example, the Q learner, or try to look at the neural networks, the deep Q learner, and try to implement the. This is the policy trade. This is model-based reinforcement learning, okay? Sorry for going over time, and let's stop here.